Hello, my name is Patrick André. I am an EMC consultant in the Pacific Northwest. I am also a member of the RTCA SC 135 committee for updating DO 160, and I would like to talk to you today about sections 16, 18, and 19, the part of the bench testing for DO 160. To begin with, there's no requirement for having a certified laboratory perform testing for DO 160, or for that matter, MIL standards 461 or 704. And as a result, many companies will do their own testing or can do their own testing. The exception is for MIL standards 461, there are laboratory requirements that are defined in section 4. Now, to perform bench testing for DO 160, which would include sections 16, 17, 18, and 19, there is no need to perform this inside a shielded enclosure. Now, most people will perform it on some type of conductive bench, although that is not necessary for DO 160G. It will be for DO 160H. Now, the conductive bench has to have a minimum size, 2.25 square meters, and it does have to have a minimum conductivity. Most people will use copper benches, but that is not necessary. You can use aluminum or brass or steel as long as it does meet the minimum conductivity. In order to do in-house testing, about the only thing that's really required is to use calibrated equipment, usually calibrated equipment that's traceable to NIST or whatever international standard you're using. That's going to be the key point of being able to perform your own testing. When you do feedback, making essentially voltage or current measurements, the instruments you use have to be calibrated. So let's get into the specific tests. For section 16, which is the input power test, there is a number of various types of tests that are performed, over voltage and under voltage. You can have various types of frequency or voltage variations and dwell times that are imposed. And there are dropout tests. Well, for example, in this case, I show a 28 volt line here that is testing from 28 down to 0 and back to 28. And you can dwell at that 0 volts for 50, 200 milliseconds, maybe a second, depending upon the category you're testing. And people will ask, well, what do I have to do? Do I have to survive through that? That's going to be a requirement that's you're going to have to define and agree with your customer or the airframe manufacturer. There may be a necessity to survive through some of these dropouts. Often they will ask for a 50 millisecond dropout that you that you can't fail or can't be disrupted during operation, but that may not necessarily be the case. So you have to agree to these type of things before you perform the tests and get them into your test procedure and have that test procedure approved by the customer or by the airframe manufacturer before you start testing, so that everyone agrees that yes, you will, or no, you won't operate through some of these dropouts. There are also various types of ramped or momentary interruptions, and some of the double dropouts that are used for digital circuits will have the separation of the two dropouts by both 10 and also you repeat it with a 50 millisecond distance between those two dropouts. In addition, there are surge tests, which are short durations, excessive voltage type tests. For example, I give one here that's for a 28 volt line. This particular category has you going to 80 volts DC for a tenth of a second, and then dropping down to 48 volts for 1 second. Now, there's no separation between those two. You have to do one and followed by the other serially. And then maybe other types of voltages, engine startup, for you starting at 10 volts and slowly increasing to 20.5 volts before going back to normal voltage. And there's other types. Category B has one where you drop out from minimum voltage, whatever minimum line voltage, down to 0 over a period of 10 minutes. So you're going to notice a number of these type of situations to try to replicate what might actually occur on the aircraft. Now, the inrush current test is really well done by the AE Techron system. The reason why is it gives you a very clean turn on without any overshoots or ringing or anything of that nature. In addition, you are allowed to have a ramp up during your inrush test. That means that you can, and the ramp up for, like, say, DC can be up to 300 microseconds, and for AC it can be a quarter cycle. Well, for 400 hertz, that's 625 microseconds. The reason why I point that out is that if you do have internal capacitance, which typically is the source of the inrush, it's the capacitors charging up when you turn on, having a ramp up time will allow those capacitors to charge a little bit slower and might give you a chance to pass that 9x, 9 times the input current, maximum input current, within that 3 millisecond window. Now, for this test, the use of a ground plane is acceptable, but it's not required. You can perform this on any bench to perform this test. However, we recommend you do not use LISNs, and that will be mandatory in DO160H. We do not want the LISNs to either distort the waveform or create an unfair advantage to you, because there are capacitors inside those LISNs that can create a holdup or distort the waveforms that we're trying to provide to the unit. So no LISNs are used on your power lines. Let me look at the momentary interrupt test here. This is from table 16.3, which is for the DC portion of the momentary interrupts. In this case, you're going to notice my table here is vertical, and we're going to provide that table vertically in DO160H. Currently, it's horizontal. It makes it a little tough sometimes to look at a test condition and look down on a table to figure out what's the fall time, the dwell time, the rise time, and to what percentage are you performing the test. Let me look at test condition 3 here, and I'll define some of this for you. So it has a fall time of 17 milliseconds. There's a dwell time at some minimum voltage for 8 milliseconds, and then a rise time for 4 milliseconds. The dwell time is not at 0. It's going to be at 15% of the nominal voltage. Well, for 28 volts, 15% is 4.2 volts. So the test should start here at 28 volts, fall for 17 milliseconds to 4.2 volts, dwell for 8 milliseconds at 4.2 volts, and then rise for 4 milliseconds back up to 28 volts. I set this up in the 3110 signal source with an amplifier and to perform this test. And here's the results. Now, there is my 17 millisecond decay time. And if you notice, that is a very smooth waveform. It isn't stair-stepped at all. It is very, very continuous. And then I have at 4.2 volts my 8 millisecond dwell and a 4 millisecond rise. Now you'll notice down here, this is 4 milliseconds per division. So there's 2 divisions here, 1 division there. And you'll notice right there, I've got my markers showing a 17 millisecond fall time to 4.2 volts. So very precisely performed and very clean waveform. If you do need to make modifications to this for whatever reason, there's possibly a customer requirement to change this, this is simple to change. You just simply change the numbers that are in this particular waveform to whatever dwell times or voltages you want to dwell at, and perform the test. It's as simple as that. Now let's jump over to section 18. This is the audio frequency conducted susceptibility test. The intent here is to assure that whatever device you have is going to be able to operate if you experience some voltage ripple, voltage variations on the input power line. Now, I want to be clear what an input power line is. What is the bus power? So this is only performed on aircraft bus power. That's going to be either 28 volts supplied by the aircraft, or it's going to be something like the 400 cycle power lines, or if you have variable power 350 to 650 or 350 to 800 hertz. This does not apply to voltages or power if it's coming from another piece of equipment. So if you have a device on the aircraft that is supplying power to you, but you're not getting power directly from the aircraft, this test does not apply to you. Okay, so when you're performing this test, you're doing frequency steps at 30 frequencies per decade, logarithmically spaced. You can see a formula here. These about 8% step sizes. And you dwell at each one of these frequencies for 60 seconds. Now we want you to dwell at each one of those frequencies for 60 seconds because we're looking for filter harmonics or filter resonances that can cause heating. And if your filter goes into a resonance and we dwell at that for a period of time, it can create a situation or an issue with your input filter. And that's what we're looking for. We want to make sure that that's not going to be the case. However, with these 60-second dwells, if you're performing the test, say, to category Z, which has 127 frequencies that you have to test from one end to the other, that's 2 hours and 7 minutes of test time. So this test is going to be a slow test. It's going to take you a while to perform. Now, historically, this test has been done by using a coupling transformer. AE Techron has a T2000. It's a wonderful transformer, works very, very well. You route your signal source, this is a 3110, let's say, into a 7234 amplifier, goes through the transformer, and that couples the voltage onto the power line. However, I was asking about this test to the committee, and I said, well, is there a reason why, especially with a situation if you have a AE Techron that's supplying the power, DC power, and it has the capability of putting a ripple directly onto the power line, can you do that? And the answer was, yeah, there's really no reason not to perform that test that way. So this becomes a bit of an advantage if you have to do a test where you have a very high power and you need to place a ripple on top of it, and maybe the transformer cannot handle that much line current. Well, now you can supply that power directly from your amplifier and put the ripple onto that. It's a very clean way of performing this test. And it can provide maybe a bit easier test setup for you as well. Now you perform the test, same sort of way. Each frequency will have the set voltage, and you can now add voltages. You can add different frequencies. You can change this thing any way you want and make it unique to your particular test. When doing this test, I always recommend, first off, do the voltage measurements as close to the EUT as possible, especially if your equipment takes a lot of current, because that wire will experience a voltage drop. And we need to assure that you're testing at full level. You also need to monitor how much current is being injected into the system. So you do need a current monitor of some type. And as a result, you're going to end up with two measurements. The current times the voltage does not need to exceed 100 watts. So if you're drawing a lot of current when you're trying to induce the voltage, there is a secondary standard or secondary limit that allows you to back off the voltage to avoid inducing excessive current. So let's take a look at section 19 now. This test has 5 different tests that are performed. 2 of them are magnetic field tests. So you have induced magnetic field into the equipment and also into interconnect cables. There are 2 electric field tests also into equipment and interconnect cables. And then you also have a spike test. That's into the interconnect cables. So what's an interconnect cable? An interconnect cable is any cable that does not have power in it. So this does not apply to input power. It can apply if your power is coming from another piece of equipment. We will consider that an interconnect wire, not a power wire. So if your equipment is operating, say, at 12 volts, and that 12 volts is being supplied by another piece of equipment, that will be part of this test. Now this test has 4 different categories, A, B, C, and Z, and it also can be performed on 3 different types of primary power. So you need to know what the primary power on the aircraft. Is it 400 hertz? Is it 350 to 650? Or wide 350 to 800 hertz? And what you're going to end up looking at is, for your test levels, are these charts. Now there are 3 of these charts. They are defined by the tests on this side here. You can see the 5 tests. There's a magnetic field test, the electric field test, and the spike test. And your 4 categories across the top here are Z, A, B, and C. But you'll notice this has the N designation here. The N designation has to do with the type of power. So there are actually 3 of these charts, one for C, one for N, and one for W. So let's say your equipment runs on 28 volt DC. Well, that's your primary power, but that may not be the primary power on board the aircraft. There will be AC power as well in most cases. And if there's AC power, you need to know what category you're going to be testing your DC equipment to. So even though you're running on DC, the information will have to flow down to you. Is it going to be a category C, N, or W? So what type of power is being used, AC power being used on board the aircraft in order to perform this test? Again, the sweep times are and sweep frequencies. You're doing another 30 steps per decade. This time, though, you're only doing it at 10-second dwells for each one of these frequencies. And you can reduce your test levels if your cables are short. Now, when we're talking about reducing your test levels, we're talking about knowing what the installed cable is on the aircraft. If you know that your cable on board the aircraft is less than 3.3 meters, then you can reduce the test levels by whatever percentage of length it's shorter. So if it's 2.3 meters instead of 3.3 meters, your test distance will go from 3 meters to 2 meters. All your testing will reduce by 33%. If you don't know how long the cable is, you have to perform the test at full level. Now, if you have a very short cable, if you know that your cable is less than 1.5 meters long, this test is not required. So let's look at these 5 tests. Here's the first one. This is a magnetic field induced into the equipment. This is typically done at 20 amps, and it's either done at 400 hertz, or if you're using N or W standards, then you're going to do it at low and high frequencies. So that'll be 350 and 650, or 350 and 800 hertz. When you perform this test, you're going to have 20 amps of current in this wire. So make sure that your current carrying wire is going to be heavy duty enough to be to handle that much current. Now, this is not dangerous to actually handhold this wire. You can actually just handhold that wire and sweep it on all sides, making sure that your distance between the cable that you're using and the unit is less than 15 centimeters. The other thing is that you're going to perform this test in 2 axes on each face. So that means left to right and up and down. So let me take a look at the top here. You're going to do it from top to bottom, and you're going to do it from left to right. So there's 2 axes, 3 on each one of these sides. You're going to do the top face, you're going to do the front face, left, back, and right face. Right or left, maybe backwards, depending upon which direction you're looking at this, I suppose. So but you're going to do 5 faces. You do not have to do the bottom. The 5 faces will have 2 axes, so there's essentially 10 tests that you're doing. And if you have to do at 2 different frequencies, 350 and 650, 20 tests. These tests, you're dwelling for 10 seconds on each face, so make sure that you are leaving an adequate amount of time for exposure in each position. Now, for the electric field induced in the equipment, you're going to be placing a 170 volts on that wire. And so what I recommend doing is using that T3700 step-up transformer and a safety resistor. It's not required, but it's really a good idea to have one there. And that safety resistor is going to be some type of high voltage resistor, and usually a high value as well, say like a 100K ohm resistor. Here's why. Since I have an open-ended wire here, if there's any exposed metal at the end of that wire and it touches ground, you could potentially short this thing to ground, which might cause some excitement, and we don't want that. Or you can touch the chassis of the equipment, and we'll definitely not want that either. So most people will take this wire, this exposed wire here, and place it inside something like a plastic metal tube, or tape it to the side of a dowel, and then tape off the ends to assure that it's not being you're creating a safety at the end of the wire. And then you again sweep all sides, front, left, right, back, and top in 2 axes, left and right, and up and down. And then you also want to make sure that you're measuring the voltage. So some type of voltmeter capable of handling 170 volts, most of them are, to assure that you've got the right level of testing. This test is not required if you have an all-metal piece of equipment or a well-shielded piece of equipment. This is designed for equipment that has an open chassis or a plastic housing or fiberglass, something of that nature. But if you have an all-metal box, there's no need to do this test. Now, often what I will end up doing is use a silicone insulated wire, and I'll use that also for some of my other high voltage tests, and I'll show you that in a few minutes here. So you want something that's safe and is not going to create an electrical problem. So now we're getting into the interconnect cable tests. This one is the magnetic field into the interconnect cable, and I'm going to have my T1000 here as a 10-to-1 step-down transformer, very low impedance on this side, capable of producing very high currents. And you take that wire and route it out to next to your interconnect cable and back. Okay, let's talk about this wire for a little bit. First off, it's possible that you're going to carry up to 40 amps or maybe more than that in that wire. That's because, say in the case of category Z where you have to do 120 amp meters, well, I've got 3 meters of exposed wire here. So to get 120 amp meters with 3 meters of exposed wire, I need 40 amps. 40 amps times 3 meters is 120 amp meters. And that's how that math works. The other thing is that you need to assure that you've got 15 centimeters between the end of the exposed cable and the EUT, also 15 centimeters between the end of the exposed cable and the support equipment. And the reason why we want to allow that is we don't want these fields that we're creating to couple into a connector at either end, because often these connectors will have wires that splay out, and those fields can get between the wires. That may be an unfair type test at that location. So make sure you're not make sure you're keeping that wire away from both connectors. The problem with that is if the group has created your cable and they made it a little bit too short, you can't expose 3 meters of wire and maintain this 15 centimeters. You may find that your exposed wire is got to drop down by a certain factor, 2.8, 2.5, maybe even, let's say 2 meters. You only have 2 meters of exposed cable. Well, if you can only expose 2 meters, then instead of 40 amps in that cable, you're going to have to bump it up 33% well, actually, you have to bump it up to 60 volts, 60 amps of current. And that's the reason why we want to use a very high current carrying cable. What I like to use in this case is 12 gauge speaker wire. This is the reason why I like to use it. First off, speaker wire tends to be very flexible, so I can keep these wires, wrap them next to or lie them next to this cable and still move them around easy enough to whatever position the transformer is. And the beauty of speaker wire is that it's what we also call zip cord. It has two conductors internally. And so now you have two current carrying conductors, both capable of carrying about 20 amps or so. And maybe you can get up to 30 amps with some caution because that cable's going to get hot. Remember that. And maybe you have to wrap it twice. So come around here, bring it over, back up, and do a second turn. Now, if you do that, you can, instead of using 60 amps, you can use 30 amps or 15 amps in each wire for that matter. And then you have an adequate amount of field strength that you can create here. So there's a number of methods you can use to assure that you are maintaining that much, getting the adequate amount of current. Now, remember that you're going to have a lot of wire here as a result, because not only do you have, say, 3 meters of exposed wire, but you also have to move these wires back a meter on each end. So there's 3 meters, 4, that's got to come all the way back to the transformer and out, so that's another 3 meters and another meter here. Well, that's 8 meters now of wire. And if you do 2 turns, you're doing that twice. That's 16 meters of wire. That can create a lot of impedance. There's a lot of wire impedance. So if you end up with only needing 1 turn, don't coil this wire up down in the corner. And I say that because if you end up with, remember I was telling you that's a low impedance output on this thing. If you do coil that wire up down here in the corner, you end up creating an inductor, which can change your impedance of your output. And if you've calibrated into a straight wire, or worse, if you calibrate it into a whole coil of wire, and then you go to run the test, you may overtest. The reason why, and I did this myself, I had that wire coiled up on the bench, did the calibration, found I needed quite a bit of power on this side to push current through that inductor. And when I went to do the final test, I had the wire straight. Well, that's much lower inductance, as it turns out, than a coil of wire. And as a result, I was trying to push the same amount of current, and I was way over testing. I just about melted the insulation off that wire. So don't coil wires either in calibration or during the test. Now, in the case of the electric field induced into interconnect cables, you are going to use a high voltage cable here for sure, because, say in the category Z, where you have to do 5400 volt meters for a 3 meter cable, that means you need 1800 volts, 1800 volts on that wire. The T3700 is quite capable of doing that, but you now have a wire that has a very high voltage on it. So please proceed with caution in this test. And again, I'll talk about using a silicone-based insulated wire for this. Your setup is going to require 3 turns or 3 wraps of the induced wire onto your interconnect cable. So there's going to be at least 9 turns from one end to the other for a 3-meter exposed wire. You're going to have, again, your 15 centimeters at this end and this end that you're not going to want to be close to the equipment or the support equipment. And then you're going to be open circuit here. Or if you want to create a more safe environment, again, use that high voltage, high value resistor, 100,000 ohms, something like that, 100K ohm resistor, and tie it to chassis. 100K ohm resistance here would be fine to keep the voltage down, the currents down if there's a problem, and assure that you're maintaining safety throughout all of this. In addition, like I said, you want to use a high voltage wire to handle that high voltage as needed, but you also want to proceed with caution on your measurement equipment. If you use an oscilloscope, most oscilloscope probes are only rated for 300 volts. So if you do this measurement with an oscilloscope, make sure you're using a high voltage oscilloscope, usually the 100 to 1, some of them are rated to 1,000 volts. Some of the 1,000 to 1s are much higher voltage, and you may have to use something of that nature to make that measurement. Multimeters do have high voltage probes that can be used as well. The exposed cable, again, 3 meters. If that needs to be reduced, you may have to increase your voltage depending upon the amount of distance that you're able to induce. Now, in the case of a shorter cable, like I said before, if it's shorter on the aircraft, you can maintain a shorter exposed distance or reduce the test level. Either one would be adequate. When we get into doing the induced spikes into the interconnect cables, again, you're going to be doing this 3 turns per meter. So what I like to do is, and I recommend this to my clients, is use that same cable used for high voltage. At this point, you can disconnect it from your resistor or whatever termination you might have for safety reasons, and connect that same wire into your chattering relay, which is the other name for the induced spikes test. So the relay coil will use the same wire as the high voltage or the electric field induced in the interconnect cables. The relay, right now, D160G does define the relay, but quite honestly, if you don't use that exact relay, if you use a different relay and you get the voltage induced spikes voltages that you need, you're doing the test properly. We are more concerned about the voltages that are being induced and not the relay itself. As a result, in DO160H, this test will be maintained, and we will be removing all the requirements on that relay. We are only looking for the voltage. We are only looking to maintain at least 5 spikes per 50 microseconds that are over 600 volts, and you're doing the test. Now, again, you're going to be measuring at least 600 volts, so make sure that the equipment you're using, again, is high voltage rated and is capable of making those measurements for you. Now, in a situation where you are testing a shorter wire, you may have some difficulty here because the only time you really can expose less wire is if your cable is shorter on the aircraft. You really have to expose 3 meters of wire. And the reason why is because it's difficult to increase the voltage on this thing. However, I do have a couple of tricks. People have had some trouble on certain relays obtaining the full 600 volts or getting enough spikes over 600 volts to perform the test. One thing you can do, and let me show you what's going on with this relay. This is powering the relay coil. The relay coil is essentially in this leg, and from there, from the output of the relay coil, it wraps around, and it comes to a normally closed relay switch here. that as you energize that relay coil, it opens up the switch. So it breaks its own contact. Well, you got a lot of current flowing through here, and all of a sudden you're opening that switch. This has to be an unsuppressed relay. In other words, there's no filter across that relay contact. As that opens, it arcs, and there's the source of your noise. Now, if you're not getting enough voltage, there's two things you can do, and maybe you want to do both of them. Number one, you can always add more wire to this because adding wire will add inductance. Or you can add more inductance in this line here. And you can experiment around how much inductance that is. It probably doesn't have to be more than 10 or 20 microhenries, but add as much as you want. And then you'll be able to provide the current the energy in that magnetic field, the induced magnetic field throughout this whole loop, that'll drive the currents across the contact harder, and as a result, you get higher voltages arcing across that contact. So that is one trick. Increase the inductance either with the wire used or by adding inductance into the power line to the relay. Now, some of the things that are going to be coming up in DO160H, we are going to mandate the use of LISNs for section 18 and 19 testing and the use of a ground plane. That'll also be true for section 17 as well, the spike test, which I did not cover in this presentation. But we will also mandate no LISNs for section 16. So expect that in the future. Otherwise, most of these tests will be the same. Section 16 got a huge rework and is greatly cleaned up. You're going to love the new presentation that we're providing in section 16. A lot of wonderful work was done by the committee, but a lot of the test levels will look exactly the same. Thank you for listening. I hope this has been helpful.